In this lesson, I'm going to describe big O notation. You can use big O notation to study the performance of algorithms. Normally, big O notation looks at the upper bound on an algorithm's performance, so you're looking at its worst-case behavior. For many practical uses, that's the safest way to look at an algorithm's performance. If an algorithm has a good big O performance, then you don't need to worry about it blowing up on you when you use it in a program. Big O notation also looks at an algorithm's asymptotic behavior. By asymptotic behavior, I mean the algorithm's performance as the size of the problem grows very large. Often people use the value n to represent the size of the problem. So another way to describe asymptotic behavior is to ask yourself, what happens to an algorithm's performance as n grows very large? For example, suppose you want to sort a list of numbers, and you have a couple of different algorithms that you could use. If your list only contains 2 numbers, so the size n equals 2, then it doesn't matter which algorithm you use. It's hard to imagine any method taking more than a few microseconds on a computer. Now suppose the list contains 10 numbers, so n equals 10. That's still not a very big list, so whatever algorithm you decide to use will be fast enough. Suppose the list contains 100 numbers, or 1,000, or maybe 1,000,000. Now things start to get interesting. It's still not all that hard to sort 1,000,000 numbers on a computer, but now the algorithm you pick might actually make a difference. Some sorting algorithms are much faster than others, so some might sort this list in a few seconds, while others might take a few hours. This is what I mean by asymptotic behavior. Big O notation looks at an algorithm's performance when the problem size becomes large, because that's usually the only time we care too much about the algorithm's performance. So how do you figure out an algorithm's big O notation? You can do that by following 5 rules. First, if an algorithm performs f of n steps for some mathematical function f, then the algorithm has order f of n performance. It's written like this, big O, paren, the function, close paren. It's usually pronounced order f of n. For example, suppose you want to find the largest number in an array of values using this simple algorithm. The algorithm initializes the variable max to hold the first value in the array. It then loops through the array of values. If it finds a value larger than max, it updates max to hold that value. For an array containing n items, the loop performs n steps. That means this algorithm has order n behavior. Here the function is simply the linear function f of n equals n. Here's the second rule. If an algorithm performs f of n steps followed by g of n steps, then it has behavior order f of n plus g of n. For example, consider this algorithm for finding the maximum and minimum values in an array of values. The algorithm starts as it did before to find the maximum value. Then it repeats roughly the same steps to find the minimum value. First it performs n steps, then it performs another n steps, so its behavior is order n plus n, or order 2n. If the algorithm performs some steps followed by some more steps, you can add the behavior of the 2 sets of steps. The third rule says, if the function f is larger than the function g for large problems, then you can simplify f plus g to be just f. Basically, this says you can round up. Because f is larger than g, eventually the function f will dominate the runtime, so you could ignore g. For example, suppose an algorithm performs order n squared steps, followed by order n more steps. The function n squared is bigger than the function n for large n, so this algorithm's performance is order n squared. To see why that makes sense, let's plug in some numbers and see how many steps the program is executing. When n is 10, n squared is 100, and n squared plus n is 110. At that point, the extra n accounts for only 10% of the total number of steps. When n is 100, n squared is 10,000, and n squared plus n is 10,100. Now the extra n term adds only 1% to the total. When n is 1,000, n squared is 1,000,000, and n squared plus n is 1,001,000. Now the extra n adds only 0.1% to the total. You can probably see where this is going. As the problem size gets larger and larger, the extra n steps contribute a smaller and smaller percentage to the total. If you were using the algorithm in a program, the amount of time spent on those extra n steps would mean less and less. For example, if n is 100,000 and the program takes an hour to run, then the extra n steps adds only about 1/3 of a second to the total. It's just not worth worrying about. Notice that this rule also means you could ignore constants that are added to a function. For example, order c plus f of n for some constant c is the same as order f of n. That's because the constant c is also a function, it just has a constant value. Because a constant is smaller than any function that increases as n increases, you can ignore the constant. That's rule 3. If the behavior depends on the sum of 2 functions, you can ignore the smaller function. Rule 4 says, if an algorithm performs g of n steps for each of f of n steps, then its behavior is order f of n times g of n. For example, this algorithm determines whether an array contains two identical values. The for-I loop loops through the array. Nested inside that loop, a for-j loop also loops through the array. Within the inner loop, the program compares the values at positions I and j. If the values are the same and I isn't equal to j, then the algorithm returns true to indicate that the array contains the same value twice. Here, the for-I loop runs through the n items in the array. For each of those items, the for-j loop also runs through the n items in the array. That means the algorithm's behavior is order n times n, or order n squared. That's how Rule 4 works. If an algorithm performs g of n steps for each of f of n steps, its behavior is order f of n times g of n. The last rule says you can ignore constant multiples. That means order c times f of n is the same as order f of n, and the order f of c times n equals order f of n. This rule is a bit harder to understand. Suppose one algorithm performs order n squared steps, and another algorithm performs order 2 times n squared steps. Even when n is large, the second algorithm will still take roughly twice as long as the first algorithm. In this case, the big O notation doesn't really let you compare those two algorithms. However, it does let you compare them to other algorithms that have different big O notations. For large n, both will be slower than order n algorithms, and both will be faster than order n cubed algorithms. In practice, you may need to experiment to pick between two algorithms that have the same runtime behavior. For example, there are many sorting algorithms that have order n times log n behavior, but some are considerably faster than others. Those are the rules for big N notation. They may seem a bit confusing now, but they should get easier after you use them for a while in later lessons. If you're a graduate computer science student, you need to apply the rules carefully and precisely. For this course, however, you can use the rules in a fairly intuitive way and still get good results. In this lesson, I'm going to describe some of the more common complexity functions that you'll encounter when you use big O notation. I'll also explain why an algorithm might end up with a particular runtime function. A few algorithms take a constant amount of time. For example, setting a variable equal to the first item in an array takes only one step. We say that this kind of algorithm has order 1 behavior. Remember that you get to ignore constant multiples when you're working with big O notation. So order 1 behavior applies to any algorithm that performs a fixed number of steps. If an algorithm performs 1,000 or even 1,000,000 steps, it still has constant runtime, as long as the number of steps doesn't change when n increases. An order n algorithm typically performs one action per input. For example, if an algorithm loops through an array of n numbers to find the largest, it has order n behavior. An order n squared algorithm might loop through the inputs and, for each input, perform another loop through the inputs. More generally, an order n to the c algorithm for some constant c usually contains c loops nested inside each other. Some of the more exotic algorithms use other powers of n. For example, some algorithms have order n to the 1/2 behavior. N to the 1/2 is the same as the square root of n. The behavior of other algorithms might involve strange powers of n, such as n to the 1.5. In general, for powers of n, the bigger the power, the faster the function grows as n increases. Some algorithms have behavior that depends on the logarithm of n. A common example is when some sort of search divides the items being searched into two pieces at each step. For example, suppose you want to find the value 17 in this sorted tree, starting from the root. You start at the root node, which has value 21, and you compare that value to the target value 17. Because 17 is less than 21, you move down the left branch of the tree. When you take the left branch, you eliminate from consideration all of the nodes in the right half of the tree. You've cut the number of possible locations where the value 17 might occur in half. Next, you compare the value 17 with the value at the new node you're visiting, 9. Because 17 is greater than 9, you move down the right branch. By moving down a branch, you've eliminated half of the remaining nodes where 17 might be hiding. Next, you compare 17 to the new node's value 15. 17 is bigger, so you move down the right branch again. The next time you compare the current node's value to 17, you find what you're looking for and you're done. By using the tree's structure, we found the target value after examining only 4 nodes with values 21, 9, 15, and 17. This tree contains 15 nodes. If we round that up to 16 for convenience, you should note that log base 2 of 16 equals 4, because 2 to the 4 equals 16. That's why we only needed to examine 4 nodes in this tree. This is the way many algorithms get their order log n performance, by climbing through some sort of tree. Before I leave the topic of log n algorithms, I also want to mention that all log bases are the same as far as big O notation is concerned. You can use this formula to convert from one base a to another base b. Here, the value log base a of b is just some constant. For example, if you want to convert from base 2 to base 10, this value is log base 2 of 10. Because big O notation ignores constant multiples, you can add whatever conversion factor you like here to change log bases. Because log bases don't matter in big O notation, people usually just write it like this: order log n without writing any particular base. Some exotic algorithms have order log n behavior. They're very complicated and hard to analyze. Algorithms with order 2 to the n behavior often make selections from groups of objects. For example, if you're dividing n objects into two groups, there are two ways you can assign each object, into one group or the other. That means the total number of possible assignments is 2 times 2 times 2 and so on, with 1 2 for each of those objects. That means there's a total of 2 to the n possible assignments, so the algorithm has 2 to the n behavior. The last runtime function I'm going to mention now is n factorial. In case you don't remember, n factorial is written as n followed by an exclamation mark, and n factorial means n times n minus 1 times n minus 2 and so on down to 1. For example, 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1, which equals 720. Algorithms with factorial behavior often involve arrangements of items because there are n factorial ways you can arrange n items. Those are the most common functions you'll see when studying algorithms, so that's all I want to say in this lesson. In another lesson, I'll compare these functions so you can get a feel for which algorithms are faster than others and by how much.